Hello, fellow kids. Today we are going to derive the kinematic equations using calculus. So, first one, the easiest one to derive. We're going to start with something we already know, that acceleration is equal to the rate of change of velocity with respect to time. The derivative of velocity with respect to time. So we are going to multiply both sides here by dt, giving us a dt equals dv, okay? And now we can integrate both sides. And over here, we are going to take the definite integral of this, actually. So we are going to integrate from some initial velocity to some final velocity. So evaluating this integral on the left will give us a times t, because since we're integrating acceleration with respect to time, we're just going to add a time term here, a linear time term here, is equal to v evaluated from vf to v naught, which is just going to be final velocity minus initial velocity. And then we can rewrite this to say final or velocity equals initial velocity plus acceleration times time. And there's our first kinematic equation. And if you check the units, it all works out. Meters per second equals meters per second times acceleration times time, which is meters per second. So now for the next kinematic equation. Starting from where we left off, v equals v naught plus a times t. We're going to rewrite velocity here as the derivative of acceleration with respect to time, dx over dt, right? Equals v naught plus at. And just like how we did over here, we can multiply both sides by dt again. So that's going to give us dx equals v naught dt plus at dt. And again, we are going to integrate both sides. So we're going to integrate this one over here from an initial position to a final position. And this will give us x evaluated from final position to initial position, which is just going to be delta x, right? Because position final minus position initial is the change in position. And this will be equal to v naught times t, because we're integrating two different variables here. We have velocity and time, so we're just going to stick that there. Plus 1/2 acceleration times time squared, because we actually have an agreement with the differential and the variable. Now we're actually going to do the whole square divided by 2 thing. And this is our second kinematic equation. Now, this last equation is a little tricky. It's not quite as straightforward or obvious as the first two, but bear with me, it's not impossible. We are going to start with another statement that we already know, but it'll be a little weird. So, we're going to start with dv divided by acceleration equals dt. You can check this out yourself. Dv divided by a is the same as dv divided by dv divided by dt, which is the same as dv times dt over dv. You can do the algebra yourself, but I'm going to have this here. And dt is also equal to dx divided by v. If you do the algebra like you did over here, it's the same thing, essentially. So, knowing that, we're going to set dv over a equal to dx over v. So dv over a equals dx over v. And we are going to multiply both sides by v and a now. So we're going to have v dv is equal to a dx. So it is time to integrate again. So we're going to integrate this over here. And we are going to integrate this over here. And we are going to evaluate this integral from some initial velocity to some final velocity. And the integral on the right from some initial position, right? Because that's the differential, some initial position to final position. So this is going to give us on the left here v squared over 2 evaluated from vf to v naught, which is just the same as saying, well, once you evaluate, it comes out to be vf squared over 2 divided by v naught squared over 2. And this is going to be equal to a times delta x, right? Because this integral would evaluate to a times x evaluated from final position to initial position, which gives us delta x. So then we can add, we can move v naught squared over 2 onto this side. And then we can multiply both sides by 2. And that will give us vf squared equals v naught squared plus 2 times acceleration times change in position. So I hope you found these derivations helpful. If you have any questions, you can ask me in the comments, because goodness knows I have nothing better to do.